Augsburg, Bavaria, 26 April 1939. Just after 6 in the morning, the grass at the edge of the airfield is still wet with dew, and a single aircraft sits at the end of the runway with its engine already screaming. Ground crew stand well back. The pilot inside, a slight, unassuming man named Fritz Wendell, has one hand resting on a throttle that is about to be pushed further forward than any propeller-driven aircraft has ever demanded. The machine in front of him carries the unmistakable silhouette of the Messerschmitt Bf-109, the fighter that within months will be dueling Spitfires over the English Channel. Painted on its flank, deliberately and misleadingly, is the designation that the world's press will soon be told to believe. But the aircraft straining against its wheel chocks this morning is not, in truth, a Bf-109 at all. It is something else entirely, built around a single piece of engineering so aggressive, so close to self-destruction, that the men who designed it called it, half-jokingly, the stupid trick. In under 2 minutes, that trick will make this machine the fastest piston-engined aircraft the world has ever seen, and it will do it by nearly tearing itself apart in the process. What Wendell is about to fly is officially the Messerschmitt Me 209 V1, a specialized record breaker with almost nothing in common with the combat fighter beyond a shared engine family and a shared propaganda purpose. But the story of how it got its propeller and why that propeller very nearly killed its test pilot on more than one occasion is inseparable from the story of the Bf-109 itself, because the same small team of engineers who solved this problem went on to fit their solution in a tamer and more reliable form to every fighting variant of the 109 that followed. This is the story of a piece of engineering almost nobody has heard of, hidden inside an aircraft whose own name was a lie, and why it mattered rather more than the number painted on its fuselage that morning. By the late 1930s, aircraft designers across Europe had run into the same brick wall, and it had nothing to do with engines. Engine power was climbing fast. The Daimler-Benz DB601, fitted to the Bf-109, could, in short bursts, produce over 1,600 horsepower in specially tuned racing form, a genuinely enormous figure for the period. The problem was that raw horsepower is useless if you cannot convert it into forward thrust, and the device responsible for that conversion, the propeller, was becoming the weakest link in the entire machine. A fixed-pitch propeller, the kind that had served biplanes and early monoplanes perfectly well, is essentially a compromise carved in wood or metal. Set the blade angle for a fast, efficient cruise, and the aircraft becomes sluggish and dangerous on takeoff, straining an engine that cannot get the propeller to bite the air properly at low speed. Set the blade angle for a strong takeoff, and the aircraft's top speed suffers badly once airborne because the propeller is now spinning too fast for the thin, high-altitude air and simply thrashing rather than pulling. Engineers had known the answer in theory for years, a propeller whose blades could twist in flight to the optimum angle for whatever the aircraft was doing at that moment. Variable pitch propellers existed by the mid-1930s, but they were crude, hydraulically slow to respond, and none of them were designed to survive what a determined engineer might do if he decided to ignore the manufacturer's safety margins entirely. That was precisely Messerschmitt's problem in early 1939. Adolf Hitler's air ministry, the Reichsluftfahrtministerium, wanted the world absolute speed record for land planes, a prestige trophy currently held by an Italian Mach-E seaplane, and for land planes specifically, contested fiercely with Heinkel's rival HE-100 program. The propaganda value was considered enormous. A German aircraft, visibly resembling the fighter already entering Luftwaffe service, smashing the world speed record, would send an unmistakable message to Paris, London, and Washington about the state of German aviation. The trouble was that no propeller in existence could survive the engine speeds required to get there.
Push the DB601 racing engine to its absolute limit, and any standard propeller of the day would either overspeed catastrophically, shedding blades at several hundred kilometers per hour, or simply stall out aerodynamically and stop producing meaningful thrust altogether. Messerschmitt's engineers were being asked to solve, in a matter of months, a mechanical problem that had defeated propeller designers for a decade. The man given the job of taming this problem was Willy Messerschmitt's chief propeller specialist, working alongside engineers from VDM, the Vereinigte Deutsche Metallwerke, based at their works in Berlin-Borsigwalde, the firm that supplied variable pitch propeller hubs to most of the German aircraft industry. Their existing product, a hydraulically actuated, electrically controlled constant-speed propeller, was already a reasonably sophisticated piece of kit, using a small electric motor and a governor to adjust blade pitch automatically so the engine always turned at its most efficient speed, rather like a car's automatic gearbox picking the right ratio without the driver having to think about it. For a standard fighter, this was already a meaningful leap forward. For a record attempt demanding sustained engine speeds well beyond the propeller's rated limits, it was nowhere near enough.
The fix the team settled on was mechanically simple and, on paper, alarming. Rather than redesigning the entire hub, they narrowed the blade tips and steepened the achievable pitch range so the propeller could bite harder at extreme RPM without the tips reaching supersonic airflow speeds and losing efficiency, a problem that had plagued earlier record attempts. They stiffened the blade roots to resist the bending forces of engine speeds nearly 40% above the standard fighter's redline. And critically, they built in a mechanical override on the constant speed governor, allowing the pilot, or more accurately, allowing Wendell, to force the blades into a flatter, more aggressive pitch than the automatic system would ever normally permit, trading long-term durability entirely for a handful of minutes of maximum thrust. Engineers in the workshop reportedly referred to this override as the dumme Trick, the stupid trick, because it deliberately defeated the very safety mechanism the constant speed system existed to provide. It was the aviation equivalent of wiring a car's rev limiter shut. It worked precisely because it was allowed to be dangerous. The propeller itself, a three-bladed VDM unit roughly 3 meters across, weighed in the region of 90 kilograms, spinning at speeds that pushed the outer few inches of each blade tip close to the speed of sound, close enough that the characteristic crack and snarl of the engine at full power was reportedly audible from several kilometers away, described by ground crew as sounding less like an aircraft and more like sustained artillery fire. Behind it, the specially tuned DB601 ARJ engine, built in a small batch at Daimler-Benz Stuttgart Untertürkheim works, ran on methanol water injection mixture to prevent detonation under the extreme boost pressures involved, a fuel system that in practical combat terms would have been hopelessly impractical, but for a 15-minute record dash was exactly what the airframe needed. Production numbers for this specific configuration were, unsurprisingly, tiny. Records suggest perhaps 4 ME-209 airframes were built to this V1 record standard, and the modified propeller hubs fitted to them were essentially hand-finished, one-off components rather than a manufactured product line, a detail that later caused genuine confusion among Allied intelligence analysts trying to work out what exactly they were looking at. If you are finding this interesting so far, a quick subscribe helps more than you know, and there is a great deal more to this story still to come. On the morning of 26 April 1939, Fritz Wendell took the ME-209 V1 to just under 4,000 meters, held it in a shallow dive to build speed, and then, with the propeller's stupid trick engaged, pushed the engine well past its official limits for a measured, straight-line pass timed by international observers.
He touched a speed of 755.14 kilometers per hour, roughly 469 miles per hour, an absolute world record for piston-engined aircraft that would stand for over 3 decades, not broken until purpose-built racing aircraft in the United States finally exceeded it in the 1960s. It is worth being precise about what that record actually represents, because German propaganda at the time deliberately blurred the line. The Reich Air Ministry announced the achievement using the designation ME-109R, actively encouraging foreign observers and much of the domestic press to believe that this was a marginally modified version of the standard frontline fighter, rather than a heavily specialized, barely airworthy record machine sharing little beyond a family resemblance and an engine lineage with the aircraft actually equipping Luftwaffe squadrons. British and French intelligence assessments from the period show real uncertainty whether the Bf-109 fighters they would soon be facing in combat were genuinely capable of these speeds, an uncertainty the German ministry was entirely happy to let fester. It is a rare, well-documented case of an engineering achievement being deliberately repurposed as a piece of psychological warfare before a single shot of the coming conflict had been fired.
What is far better documented and considerably more consequential for the air war that followed is what happened to the tamer, non-suicidal version of this same VDM constant speed technology once it was refined and standardized for the actual Bf-109 fighter line. Early production Bf-109s, the B and C variants, still used simple two-position or fixed-pitch propellers, and pilots and Luftwaffe evaluators consistently noted the poor takeoff performance and mediocre climb rate that resulted. From the Bf-109E onward, the lessons learned in developing the record-breaking hub, minus its most dangerous override features, were folded into a production VDM electrically controlled constant-speed propeller fitted as standard. The effect on the fighter's real combat performance was immediate and measurable, improving climb rate meaningfully and giving pilots an automatic system that adjusted blade pitch throughout a dogfight without requiring manual intervention, freeing them to concentrate entirely on flying and shooting rather than managing engine settings, a genuine tactical advantage during the frantic seconds-matter engagements of 1940. It is worth comparing this German approach directly with what Britain and the United States were doing at the same moment, because the contrast is instructive. Royal Air Force Spitfires and Hurricanes went to war in the summer of 1940, still largely equipped with two-pitch de Havilland propellers, essentially a coarse setting and a fine setting with nothing in between. A genuine handicap that RAF pilots and engineers recognized almost immediately once combat began. It was not until the mass retrofitting of Rotol constant speed units, beginning properly in mid-1940 and accelerating through the Battle of Britain itself, that British fighters caught up with the automatic, continuously variable pitch control that German fighters already possessed as standard equipment. American aircraft, largely fitted with Hamilton Standard or Curtiss Electric constant-speed propellers, were broadly comparable to the German system in capability by the time the United States entered the war, though American units tended to favor hydraulic actuation over the VDM's electric motor design, a difference in engineering philosophy rather than a clear advantage either way. What made the German system notable was not that it was unique in concept. Constant-speed propellers were being developed in parallel by several nations, but that Messerschmitt and VDM had pushed the underlying technology to its absolute limit in full public view, generating enormous technical knowledge and enormous propaganda value from a project that was never intended to see combat at all. The genuine historical impact of this episode sits somewhere between the material and the psychological, and it is important not to overstate either side of that ledger.
Materially, the refined constant-speed propeller made every Bf-109 from the E model onwards a measurably better fighting machine than its early siblings, and that improvement mattered across roughly 30,000 Bf-109s eventually built, making it the most produced fighter aircraft in history. Psychologically, the deliberately misleading Me-109R announcement achieved something arguably just as valuable to the German war effort in 1939, seeding genuine doubt among Allied planners about exactly what they would be facing, doubt that persisted in fragments well into the early stages of the war. Whether that doubt changed a single tactical decision in the skies over Kent or Calais in 1940 is impossible to prove from the surviving record, and any historian claiming certainty on that point is overreaching. What can be said with confidence is that the aircraft itself, the actual Me-209V1, survives today only in photographs and archival film. The airframe did not survive the war. Its record-breaking successor design, the Me-209-2, never entered production at all, rendered obsolete by better solutions elsewhere. The propeller lineage it helped refine, however, lives on in surviving Bf-109 airframes held in museums from the Imperial War Museum Duxford to the Deutsches Museum in Munich, quiet metal witnesses to a piece of engineering that was, by design, never meant to be entirely safe.
Return for a moment to that Bavarian morning in April 1939. A small team of engineers, unglamorous men working in a Berlin suburb, had taken a piece of equipment everyone agreed had a sensible operating limit and had built in a way to deliberately, knowingly ignore it. They called their own creation stupid, and they were not entirely joking, because a governor override that lets a spinning 3-meter disc of metal exceed its design tolerances is exactly the kind of idea that ends careers and occasionally ends lives. It worked. It worked well enough to set a record that endured for over 30 years, and well enough, in its tamed and production-ready form, to make the ordinary fighting Bf-109 a meaningfully better aircraft than it would have otherwise have been. It worked well enough that a government happy to lie about which aircraft the record even belonged to had, underneath the lie, a genuinely remarkable piece of engineering to point to. There is a temptation, telling stories like this one, to reach for easy grandeur, to call every wartime innovation a game-changer and every engineer a genius, and that temptation should be resisted here as much as anywhere. The Me-209V1 did not win the Battle of Britain. It did not shoot down a single Allied aircraft. What it did was solve, in the space of a few frantic months, a genuine and difficult mechanical problem, using a solution its own creators privately regarded as reckless. And in doing so, it quietly improved the performance of the aircraft that would go on to be Germany's principal fighter for the entire war that followed. The record it set stood by the sheer brute confidence of engineers willing to override their own safety margins in pursuit of a number. The name painted on its fuselage that morning was a fiction. The engineering underneath it was not. And that, in the end, is the more interesting story. One small team, one dangerous override, and one propeller that very nearly tore itself apart to prove a point that decades later still stands.